All right, section 9.7 is Taylor series. And we're going to talk at least a little bit here at the beginning where in the world this series is coming from, how it's developing, and what we're going to be working with and why. So a Taylor series, well, to start with, one reason for considering series is they're an essential means for exploring and computing with transcendental functions. That was quite a loaded sentence. So let's start with transcendental functions. Do you know what those are? Do you remember? Can you give me an example? Let me ask it that way. Does anybody remember an example of a transcendental function? Okay. I'm going to give you several examples. One example of a transcendental function is sine of x. Another is cosine of x. Lest you think that they're talking about trig functions, e to the x is also transcendental, as is the natural log of x. These are all classified as transcendental functions. So these are the types of functions that we're going to be looking at. So I'll talk a little bit more about where they come into play in a minute, but they are the ones we're going to be looking at. So if we suppose that we have a power series, and this is the same power series we looked at from the last section, same notation, it has a radius of convergence r greater than 0, which means that it converges from c minus r to c plus r. And what we're going to do is we're going to take this series and we're going to take some derivatives. So in particular, you've seen this first one before. So just write that down, the part that's above my red box. All this is the notation from the power series that we encountered last time. Okay? B sub 0 plus b sub 1 times x minus c, b sub 2 times x minus c squared, and so on. And I've written down the first five terms actually, if you count the b0 on there, because it'll be easier to see what's happening with a few more terms than maybe I normally would have written had I written it out in the last section. And so what you're doing after that is you're just taking derivatives. So if this f of x is our function, then when I take the derivative, the constant term b0 in the front goes away, right? And then I'm looking at this b1 times x minus c, and you might be tempted to do some distribution, but there's really no need. The reality is that inside of this x minus c, its derivative is 1, right? So I only get the b1 still left. So b1 is my first term in the derivative. And then everything after that has power rules and chain rules. But the power rule, bringing the coefficient, or the exponent down as a coefficient, will bring down the 2, the 3, and the 4 here. And all it does then is decrease the exponent by 1. So instead of this being x minus c squared, it's now x minus c. And while there is a chain rule, we don't really have to worry too much about it because the chains inside the derivative is 1. So it's very clean. So the first derivative just looks like this. F prime is b1 plus 2b2, x minus c, 3b3, x minus c squared, and so forth. We can do that again for a second derivative. And if we do that again with the second derivative, we've got the b1 is going to go away, and I've got 2b2 left. And then while I could actually multiply out this 2 as the exponent of x minus c times the 3 and get 6, because of where I'm headed, it's going to be more helpful to me to write it as multiplication and leave that multiplication notation there. So you see this written as 3 times 2, right, instead of the number 6. There's that b sub 3, which is a coefficient. You've still got x minus c now raised to 1 power less, so it's raised to the power of 1. And then the next one is 4 times 3, b3, x minus c squared, and so forth. The third derivative, the b2 term, goes away. And I just have this 3 times 2 b cubed, or not b cubed, b sub 3. And then I've got 4 times 3, and then it's now times 2, because that was the exponent, 2, times the b sub 4, x minus c. So we're just taking derivatives. And because this is an infinite series, sorry, that's on my page before, it's an infinite series, we can do this infinitely many times, agreed? So this is only going to work if the function that we're working with actually is something that has infinite derivatives, which is sort of important. We'll come back to that thought in a little bit. But notice this doesn't even make sense if we talked about, for instance, a polynomial. it doesn't have infinite derivatives. At some point, it zeroes out and you're done. Okay? All right, so what I want to do is for us to evaluate each of these at x equals c. The nice thing about evaluating at x equals c is that all of the terms that have x minus c, they cancel out, they go away, right? They become 0. So I'm only going to have the very first term, right? So if I put in 0 into f of x, I get b0. Not 0 into f of x, c into f of x, I get b0. And if I put c into f prime of x, I get b1. If I put c in here, I get 2b2. And if I put it in here, I get 3 times 2b3. Now, in particular, if you take a look at that, and you can take a look at the next term, were we to do it for a fourth derivative, would have 4 times 3 times 2b4. You start to see a factorial, which is why I didn't multiply them out. So we actually see that f of c is b0, f prime is b1, 2b2, 3 factorial b3, and likewise the next one, like I said, would have been 4 factorial b4 had we written it out, and that would have been the fourth derivative. Here, at c. We don't see this used too much in Calc 1 and Calc 2, but remember, if you have a derivative higher than a third derivative, we write it sort of as an exponent, looks like, but it's in parentheses because it's not an exponent. But it just tells us that if that number were a 5 in that set of parentheses, it would be the fifth derivative. If there were 6 in that parentheses, it would be the sixth derivative, and so forth. So that little 4 that I wrote right here is a fourth derivative. So the fourth derivative would be 4 factorial. All right, so in general, that means that the kth derivative would be k factorial bk when we evaluate at c. And if we take that equation and we solve it for b sub k, we find out that b sub k equals the derivative, the kth derivative at c, divided by k factorial. And this works for for the k values being 0, 1, 2, and so forth, just like our summation that we're talking about. And lo and behold, there's that language that I talked about just a minute ago that says, now suppose we think about this starting with an infinitely differentiable function, i.e. a function that can be differentiated infinitely many times, like sine, cosine, or natural log of x, or e to the x. Transcendental functions, right? If we're working like that, then we can construct the Taylor series. So the Taylor series is exactly the summation from k equals 0 to infinity of that kth derivative evaluated at c divided by k factorial times the x minus c to the k. This is a power series, right? X minus c to the k. And then you should be aware of the Maclaurin series simply because it's a very specific example of a Taylor series. It's the case when c equals 0. And so we evaluate the point here of the kth derivative at the x equals 0 value, and then we just end up with x to the k since c was 0. All right. Oh, sorry. A few of you are still writing. Am I good to go to the next slide? All right. So we're going to do an example, and the first example is going to, in fact, be a Maclaurin series. Maclaurin series are perhaps the most friendly, simply because evaluating at 0 is friendlier than evaluating at most other values. So it's kind of nice. So what we're going to do is we're going to actually find several derivatives, okay? And then we're going to construct the power series notation for this function, cosine of 2x in this case, all right? So we need to find several derivatives. We're going to find f prime of x I think we'll find 4 of these. Looks like that's what I have written down. All right, so what's the derivative of cosine 2x? Good, negative 2 sine of 2x. So just to remind everyone, where in the world did the negative come from? Where did the 2 come from? Probably everybody's good with the fact that sines and cosines switch places every time, but can you remind us? 2 comes from the chain rule, so the 2 is coming from the derivative of the 2x on the inside. Good, and the negative? Yeah, when we work with the cosine, the derivative is negative sine. Yes, very good. All right, let's do the second one. Second derivative. Oops. What's the second derivative going to be? Yeah, and it'll be negative 4, right? Because it was already negative to begin with. The derivative of sine is cosine, so the sign won't change this time. How about a third derivative? Yes, this is now a positive, right, Hannah? 8 sine of 2x. How about a fourth derivative? Excellent, 16 cosine of 2x. This is nothing compared to that quiz some of you have taken, right? Easy stuff. But we want to evaluate this where the Maclaurin series is evaluated, namely at the x value of 0. So we're going to evaluate each of these, including the original function, at 0. And because sines and cosines are so friendly when evaluated at 0, some things are going to simply disappear. All right, so what is the cosine of 2 times 0? That's 1. What is negative sine of 2 times 0? That's 0. How about this? Oh, sorry, my notations were left off here. I was getting carried away. How about the second derivative at 0? Yeah, it'll be a 4 like this. Good. Yeah, sorry. Negative 4. Good. How about the third derivative? Back to 0. In fact, every other one's 0, right? Because every other time I'm turning this into sine, and sine of 0 is 0. How about the last one, 16 cosine 2x? That's 16. All right, so a couple of things to notice. I already said one of them is that every other term 0. What about the terms that are not 0? Can you predict what's happening on those? They're exponential. That's very important, and we're going to get that part too. There's something else too. They're switching signs. Yeah, it's alternating, right? They're going to switch between positives and negatives because that's what happens when we take derivatives of sines and cosines, is that every time we have a cosine, it's going to change the sign to a negative sign, opposite sign it was. All right, so a few things then. Taking a look back over here, what we're doing is this is the numerator, either case we're looking at, it's the numerator of what we're working on, right? Whereas the denominator is whatever kth term we're on with a factorial. So I'm going to write out what this series would actually look like if I'm writing it out with those pieces in there. So the first one is actually going to be the first number we got, which was 1. And in theory, it's over 0 factorial because I'm starting at 0. So I know that's 1, but just for the sake of writing it out, I'm going to write it out this time. The next one doesn't have a term, but the next term I do have is at the second derivative. So at the second derivative, I have I'll put the negative here and put the 4. What's going to be in the denominator? 2 factorial, exactly. Now coming back over here, the other thing I'm going to have is I'm going to have an x to the k power. I'm sorry, I didn't write it on the first one because k was 0. It's k to x to the 0 power, so it's 1. But this one right here, the kth term that I'm on is actually the kth term of 2, right? So this is k equals 0, k equal 1, k equal 2, k equal 3, k equal 4. That's what we're working with here. So I've got an x squared on this term. The next term is positive, and it's 16 over what? 4 factorial, and then the x to the 4th. And this will continue. Let's do the next one just for fun and see if you could figure out what it should be without actually writing out the terms. What would the next one be besides being negative? I already told you that. What should it be? Yep. Very good, Micah. Thank you. Okay. Is everybody okay with that? So these are powers of 2 on top, or powers of 4, depending on how you're thinking about them. And we notice that we've got only the even powers, right? I don't have x to the third or anything like that. And I notice that the signs are alternating. What I need to do is I need to write a series notation, a sequence notation for what's happening to this sequence. And there's probably more than one way that we could condense this and write this. In fact, I can think of at least a couple. So we've got some options on the matter, but some suggestions. Let's deal with one piece at a time. Let's just deal with the numerator. How do I get the numerator to go from 1 to 4 to 16 to 64 with powers? Because that's what you guys told me you saw before. It's powers, right? So what do I do on the numerator? You could, but 4 to the k would be better. If we do 2, we'd have to do 2 to the 2k. So either 4 to the k or 2 to the 2k, because we don't have all powers of 2, right? We actually have powers of 4. You guys with me on that one? You're looking confused at me.
Yeah, because wouldn't that take 2 there, so you get 2 to the 4th there, wouldn't you?
That was at k equals... how did I write this? I was looking at that before. Oh, I know what you're saying. Yes and no. So when we were creating these k equals 0, 1, 2, 3, 4, and so forth, that's how we created to write our sequence out right here. The problem is that when I put it back into that notation, the k has to iterate consecutively. I can't only iterate k values that are even. So that's a good point. I didn't even think about that being the case at this point. But this is my k equals 0 term. This is my k equal 1 term. This is my k equal 2 term. This is my k equal 3 term in terms of turning it into a series. Are you guys with me on that? I know I just changed what k meant right in the middle of class, which is not so cool. But unfortunately, that's what's happening on this one simply because we had all those 0 terms canceling pieces out. Yeah. Yes, yes. Okay. So I do, in fact, have a 4 to the k on this one because that k is iterating consecutively. This is a summation from k equals 0 to infinity. How about we do the denominator? What in the world's happening on my denominator? Because it's not k factorial. Why not? Yeah, I don't have the odd terms, right? I don't have a 3 factorial down there or a 5 factorial. So how in the world am I going to get it to be only even numbers in the denominator? Factorial. Right. So my denominator will be 2k factorial, right? And then after that, I've got x to a power. But again, just like on the factorials in the denominator, the powers are all even. So what will the exponent be on x? It will be 2k. There's only one more thing I have not dealt with. Do you know what it is? The alternating signs. Exactly. So far, everything I've written down is a positive. I need the signs to alternate, so let me give myself a little bit of space to do that. So whenever you're dealing with alternating signs, you know you've got -1 to a power. You just have to make sure it starts with the positive sign or the negative sign. It should. Our series is supposed to be starting at a +1, right? So my exponent's going to be one of two things. It's either k or it's k plus 1. Which one do I need? I need to have what? K. Because my k value starts at 0. So if I let k equal 0, this -1 to the 0 will in fact be a +1. Okay, everybody good with that? All right, so this is the power series I was supposed to find, the Maclaurin series specifically. This is my Maclaurin series. But it didn't ask me just to do that. It also said to find the interval of convergence. But you know how to find intervals of convergence. You just did that, or at least you will do it soon on your homework from section 9.6. Do you remember what test we used over and over and over again in that section? Ratio test. So we're going to use the ratio test. So from the ratio test, we're going to look at, all right, we consider the limit as k goes to infinity, or you can use n if you want. I think your book kind of alternates back and forth at this point, of a sub k plus 1 over a sub k and the absolute value. So that's what we're going to be writing out. So the sequence itself is right up here. I can ignore the negative 1 to the k because that gets removed when I'm taking absolute values anyway. So I'm really just looking at the 4 to the k over the 2k factorial and the x to the 2k, right? All right, so k plus 1 is going to be all of that with the k plus 1 in that spot. So I have 4 to the k plus 1 times x to the 2k, actually plus 2, because I'm going to distribute the 2 through, all over 2 times k plus 1, so that's 2k plus 2 factorial in the denominator. That's the a sub k plus 1 term. And I'm going to multiply that by the reciprocal so that I don't have to write the double fractions going on here. So that's going to be the exact fraction that I started with, 4 to the k, which is now in the denominator, x to the 2k also in the denominator, and k factorial in the numerator. And all of that needs absolute values. With the exception of the variable x, everything inside those absolute values is already positive, right? So the only part that's really going to be possibly negative anyway is that x to the 2k plus 2, or the x to the 2k in the denominator. We can start simplifying some stuff. What do you see that can simplify? Give me one thing. 4 to the k. All right, so I've got 4 to the k plus 1 here, and I've got 4 to the k. So tell me what that's going to leave me with and where. Excellent. I've got a 4 left over on top. What else can simplify? How about the factorials? 2k plus 2 factorial, all that is 2k plus 2 times 2k plus 1 times 2k, and it keeps going down from there. I'm sorry, I'm missing a 2 up there. Maybe that's why y'all were looking at me weird.
Yeah.
There we go. That looks better. And I'm going to pause, of course, when I get to the 2k factorial, because that now matches what I just changed the numerator to be, because that's what it should have been to begin with. Is that okay? So I've got some expressions.
So it gets reduced to just 2k plus 2 times 2k plus 1?
Right.
Oh,
Yeah, this part that's in purple, the box, is actually written as this way. And then, like you said, the 2k factorial is going to reduce with that 2k factorial here. So those pieces are going to go away. I get 2 terms here because I multiplied by 2. That's why I've got 2 terms still sort of remaining in the problem. So now I have the denominator here. In fact, I'll give myself some more space. My denominator here, it's going to have 2k plus 2 and 2k plus 1 in it.
Then on the top, you just have x squared.
Right. So I can change that expression a little bit differently to help us out here too. Let me use a different color. So this right here can be changed to recognize that this is x to the 2k times x squared. It's property of exponents. I can separate those out. And then just like you said, Cameron, I can then have these x to the 2k's reduced so that I've just got x squared on top. All righty, how are we doing? Everybody good? All right. I mentioned before that the only thing that stood any chance at being negative was the x. And that's true. I mean, x could be negative, but I don't really just have x in the problem any longer. I have x squared, and that's positive, so I don't have to worry about that. The other thing here is that the 4 and the x squared, neither one, actually change as k goes to infinity, right? Those are constants. At least they don't change with k. I mean, x is not a constant, but it doesn't change as k iterates. So we could think about this kind of like, and we've done this before, although it's been a little while, like the very beginning of the semester, as being able to pull these out in front because they aren't affected by anything. So I really am just doing the limit of 1 over 2k plus 2 times 2k plus 1. And what happens? I mean, what is that limit value? That's 0. So in essence, I really have here 4x squared times 0, which is 0. If I'd gotten a 1, I would have to multiply it, but I didn't, right? I've actually got this equal to 0. This is a ratio test. What's the ratio test telling us? What was the purpose? Right. Had to do with whether the value we get after we do this limiting is less than 1 or not. And this one is. So tell us what you remember. If it's less than 1, what happens? It converges absolutely. And for everything, because I don't have an interval. No, this did not depend on what x was. X could be anything I wanted, right? And it didn't make any difference. So this converges. And you're right, it converges absolutely. It converges from negative infinity to infinity. I can't remember. Oh, I think I have space. No, I don't. I used my space up. All right. Let me write it over here so that I can write it down. So by the ratio test, this converges and would, for any value of x, right? Which means that x has the interval of convergence. So hence the interval of convergence is negative infinity to infinity. And it didn't ask us on this, although if it did ask us, we could also state then what's the radius of convergence. Infinity. It sounds weird, but yeah, the radius of convergence is an infinity. Okay, what do you think? It's almost like we started with the power series, but we started one step ahead, where we actually had to create the series and then identify the pattern that put everything into it, right? I mean, that's really what we're doing. We're working with the power series here, but we're doing this one step ahead where we had to actually create the power series we're working with. All right, we're going to do another one next time that's actually going to be centered not at 0. It's going to be centered at c equals e, and we'll see how that one plays out.